lecture 3, where we'll go back to our cube that we've cut. Sorry. All right.
Sit on the table if you want.
All right, thanks. All right, so let's continue with lecture 3, where we will calculate, hopefully by the end, the principal normal stresses at that arbitrary location P based on some equations that we will derive from our cut stress cube. All right. So I'm going to draw it back up again. Okay, so here's our cube, or sorry, our cut cube. And we can start to define some terms, because that's going to help us to define the stress on this plane, right, that we have cut. So if we draw a point on the plane, I'm just going to draw some hash marks so we know it's a surface. So if we're at a point on the plane that is defined from the surface normal, all right, so here's the normal, it comes through. At that point, we can have forces in 3 directions. Uh-oh, one moment. I'm not sure what happened there. Okay, we can have forces in X, Y, and Z. So I'm going to draw those here. So like come out here. So we'll have Fx going this way, Fy, and Fz. Okay. So those are our 3 forces. And each of those forces can be thought of as the sum of all the other forces that are on this cube, right? So I mentioned in the end of the last lecture when we set up this problem that we still had our stresses, right? Sigma z, here we had sigma y, and then on the back face, sigma x. And then we also have those 6 components of the shear stress. So each of our forces there can be described as the sum of those. So I'm going to write that equation first up here at the top. So, right, the force in the x direction is obviously going to be sigma x times the area of the x face plus sigma, oops, sorry, not sigma, tau. So then we'll do tau xy times the area of the y face plus tau xz times the area of the z face. Okay? And so this is just from sum of forces along the x direction. Right? Let me draw that over here just so that it's clear. So sum of forces in the x direction equals 0. And so if we have a force on the face, then we're looking only at the x direction and the shear stress components that act in that way. So tau xy, tau xz. And then in order to get a force, we multiply a stress times an area. So in this case, we'll have ax, ay, and az, where ax is the area of this back face, right? So if we have the z, y plane, and we just look at that projection, that one is ax, right? And then if we look at the yx projection, that would be az. And we can do the same thing. So it's just these areas are the ones that span between 2 of our axes, right? On the part of the cube that we did not cut. Okay. So we could write that for all of the force components acting on the cut plane at the point that we're looking at that surface normal. Okay? I'm only going to do the one axis for some of these calculations because otherwise it's going to be too many equations. Okay? So if we start with that, then that can start to help us define the stress state. Okay? But we have those angles we defined from the origin. And so in order to get these projections, like let's say the area AX or the area AY, we need to know what those angles are in order to get those projected areas. So I'm going to define the angle. So alpha was the angle between the surface normal and the x-axis, right? That was alpha. And so we're going to call cosine alpha, which is the projection we care about, we're going to call that L, okay? So we're just going to define that so we don't have to keep writing cosine alpha, cosine alpha, cosine alpha. And then we're going to do the same for the other directions, right? So between the surface normal and the y-axis was beta. So cosine beta, we're going to call M. So we're going to have L, M, and N for the different axes. Yes?
How do you know there's no shear force on that diagonal plane that's affecting your submission forces?
How do I know there's no shear forces on the diagonal plane? So I'm not sure exactly what you mean. We do have shear stresses up here that are going to contribute to the force vectors on that plane.
Could there not be a shear on that face that you did not add to that submission forces? That's an X component?
So this Fx, Fy, and Fz includes those forces. So when we split up the stresses, we have normal stresses and shear stresses. But stress is force over an area, right? So that's the definition of stress. So here, like think back to like when you first started drawing free body diagrams, right? And in 3D space, if you chop something on that face or at that location, you can have Fx, Fy, Fz, right? So you don't deal with shear. Well, you do have shear forces, but these forces here are a combination. So like Fx, Fy, and Fz should encapsulate all of that. Does that make sense? Okay.
Is it for the balancing of the forces that you got of the part of the view? Is that one? The effects of one?
Yeah, so those are reaction. You can think of those as reaction forces, yeah. Because if we sum all the forces along, so if you go back and think about like, whatever, Newton's first law, right? We don't sum stresses to zero. We sum forces or we sum moments, right? So in order to apply Newton's first law to this, we have to work in the force space, right? So, but what we care about is stresses for this class. So that's why we're transforming between sort of stresses and forces. So if we apply balance of forces, we get an expression of a combination of these stresses and areas, right? Okay, does that make a little more sense? Okay, so if we keep moving forward, we can also define for gamma, right, which would be the angle between the surface normal and the z-axis. So cosine gamma, we're going to call n. So I'm going to kind of do like a little box here so that this is a little bit more clear. And so moving forward, we're not going to just keep talking about cosine this, cosine this, cosine this. We'll talk about L, M, and N. Okay, so the first thing we can do is go back and determine or write something down for these projected areas, AX, AY, AZ. Okay? Because what we want to have is the area of the cut plane, not necessarily all of these different areas. So we're going to think kind of in a little bit more of a vector space, and we're going to define AX is equal to A times that lowercase l, which is cosine alpha. The area in area y, come back, is AM, and the area in Z is AN. Okay, so this is kind of just geometric manipulations. So then if we go back and write an expression for fx, right, before the first term was sigma x times ax, now it's going to be sigma x times al, and then we'll add on to that tau xy times am plus tau xz times an. Okay. And you can see that we could factor out a now. Okay. So we can do, I'll just do it so that we all have the same equation. So sigma x L plus tau xy m plus tau xz n, like that. Okay. And we can do this for fy and fz, right? We just have to follow through the same formula. And so what we want to do is eventually get to some stresses. Okay. So now let's define, instead of fx, we will define the stress. I'm going to call it Sx, and that is going to be in the x direction on that cut plane. Okay, so it's going to be the force of x that we just defined divided by the area of that plane. And we already factored a out, so that's very helpful. So now we are left with sigma x times L, basically the same expression that we have above, plus tau xy m plus tau xz n. Whoops, we don't need the parentheses. Okay, so this is getting a little bit neater now, right? But we want these components in the normal direction to that cut plane, okay? Because then we can describe it as like a stress and a vector rather than all of these different components, okay? And we can, sorry, I forgot to say, we could also write the same thing for SY and SZ, okay? And so each of these stresses now, which is associated with our coordinate system, has a component that goes in the normal direction straight along our unit normal through our cut plane. Okay? And we're going to use the same geometry with the L, M, and N and the cosine projections in order to get that. Okay? So I'm going to come over to this middle section, and I'm going to write Sx, and I'm going to put an N on it. So this is the stress based on f of x on that cut plane, and it's the component going in the normal direction. Okay, so we're going to define that as L, which was our cosine alpha, times that stress we had. So it's kind of like two cosine terms together now. Okay, because we have all of these components that involve maybe some angle, but now we want the direction in a specific way, right? So we're going to take another projection, and so we're going to write that as, now it's going to be L squared sigma x plus Lm tau xy plus Ln tau xz. Okay. So I'm going to draw like a little box around that. Okay. So we have three terms, right? And so you can see now it's a combination of, we have two cosines when we're talking about sigma x, but the other ones, we have tau xy, we have now L and M. So now we have the angles that are associated with alpha and beta, or x and y directions, in that term with tau xy. So it kind of makes sense. And then L and N, which are the angles in x and z, with the term with x and z. Okay? And we can write that now for each of the other components as well. And then if we add all those up, that's our direction of stress coming directly out from that cut plane. So that's what we're going toward. So that's going to be called our normal stress at the cut plane, just sigma n. Let me write a little bit bigger here. Just have that cross out. Okay. So it's going to be Sx in the normal direction plus Sy in the normal direction plus Sz in the normal direction. And so I will write that entire thing out here. Sigma n is equal to L squared sigma x plus m squared sigma y. So I'm expanding this out to have all the terms in all directions. Plus n squared sigma z plus 2lm tau xy plus 2ln tau xz plus 2mn tau yz. Okay, so I'm going to pause there for a second. Let me know if I have made any errors that you can see easily here. All right. So for this is helpful, right? So at any arbitrary plane, we can define it with any angles we want to get L, M, and N. And then if we know what our stresses were on the cube in the first place, we can calculate the stress at that cut plane in the normal direction straight out, right? So this is, helpful if you want to say what is the normal stress at some arbitrary angle, right, within there, okay? And so that's, it can be helpful, but really what we're going to use this for is to figure out what the principal stresses are, okay? So principal normal stresses, or what's just called principal stresses, are the normal stresses on planes where the shear stresses are 0, okay? So we're going to think about this in sort of Moore's circle terms, okay? So at the beginning, we had our stress cube, right? And it was oriented along the XYZ axes, and that was our frame of reference. Okay. Well, what if we took all of the components that we had, right? Sigma x, sigma y, sigma z, all the tau x, y's, and all that, and then we wanted to know to what extent we needed to rotate the cube, or what angles we needed to rotate the cube, such that we could maximize the sigmas, right, on those planes, right? So if we rotated that whole cube, right, we could do it something like that. My drawing is not so good, but we'd rotate the whole cube in 3 dimensions such that based on our sigma x, sigma y, sigma z, and all the taus, we would get something that had maybe only normal stresses, had no shear stresses, right? So we could rotate it such that that would be the case. So when we do that, those are the principal stresses. Most of the cases that you have studied in the past, what we do is we just align our coordinate system with what we know will be the principal stresses, and then we don't have to worry about this, right? So that would be like beam theory or something like that, right? Where you just align your coordinate system with your problem, and then you don't have to transform too much, right? You may have to use Moore's circle to sort of see if there's a combination of stresses, or if you want to, figure out what the principal stress is, but you only know it's applied shear, something like that, okay? But what we're going to do here is we're not going to simplify that out at first. We're going to come up with a general equation, and then we're going to start slashing terms such that we arrive at the simplified expressions that you've probably used in the past. Okay? The planes that correspond to these rotation angles, right, which is basically the plane that we cut through. Like if I take and I say on here, there's some sort of plane that I've cut through, right? And that plane corresponds with how I've rotated my cube, right? Then that would be the principal planes. Okay. So for any stress state in 3D, we can find a rotation, right, where there's no shear stresses anymore. It's all normal stresses. Those are called the principal stresses. And the planes on which they act, which are described by geometry, right, which we had L, M, and N to describe our rotation angles, those are called the principal planes. Okay? And so this is the background for like problems in elasticity and things like that. Okay, so let's use what we know about this normal direction stress and have a postulate that I just told you about, which says that the cut plane is a principal plane. Okay, so that means that our surface normal, right, is going to be one of these principal normal stresses, and we will have to determine what the direction cosines are, this L, M, and N, in order to achieve that. And when we're doing that, then we'll be able to solve for all three principal stresses, and we will be able to solve for them in terms of the stresses that we had at the beginning: sigma x, sigma y, sigma z, tau xy, tau xz, tau yz. Okay? And so that's what we're going to do next, and we'll get a general equation that will be useful. So before we had defined, f of x, and we had a times L, right? That was our a of x, times sigma x plus am times tau xy plus an times tau xz. Okay? And now we don't have any shear stress. We're saying that we are looking for the L, M, and N at which these go to 0. Okay, so we're going to cut off those two terms. And now we're going to say that we have f of x in this kind of a normal direction is a times L times sigma. Okay, and so we no longer have like sigma n or anything like that. We're going to define this sigma as our principal shear stress. Or sorry, not principal shear stress, principal normal stress. So now we don't have any other shear stresses in there in that rotation. Okay. Similarly, before we had stress in that x direction of L times sigma x plus m times tau xy plus n times tau xz. Okay? And now we're saying, oh, no more shear stresses. So now we're reduced to stress due to f of x in our normal direction is just L times sigma. So this is getting a little bit simpler now. Okay. So now we have these two expressions, and what we usually we don't want to lose all of our inputs, right? Our sigma x, our sigma y, our sigma z, all of these inputs. But what we want to keep is now this sigma that we are on the hunt for, we're looking for. So we're going to equate these last two expressions in order to do that. So we're going to take this expression that we had before, and then our new expression where we have no shear stress, and we're going to set them equal to each other. So we're going to come out with this. So we're going to come out with L times sigma, that's the bottom expression, is equal to the right side of that upper expression. So L sigma x plus m tau xy plus n tau xz. Okay. So this is the expression for our x direction, right? So we've just been working with one axis, so we don't have like a million equations and we're losing track of everything. Okay. We can also write this same expression for y and z. Okay. And it's going to, I'm going to change it around just a little bit first before I show you those other ones. So I'm going to change this around to where it equals 0. So we're going to combine like terms with L, and then we'll have it all equal to 0. So if we have L as a coefficient, we have two things multiplied times that. We have sigma and we have sigma x. All right. And in this case, we want the first term positive, so we put everything on the other side. So then these terms go negative like this. But the signs work out. Okay. So we can rewrite it like that. And then we can write the same type of expression for y and z. Okay? And then we'll have three equations that are in like a system of equations that all have the same variables in them, which are sigma x, sigma y, sigma z, tau xy, tau yz, tau xz. Okay? And when we do that, I'll write it on the next slide so that you can see them all. So in x, just so that you can have sort of a feel for it. So we have L sigma minus sigma x. This is the same expression I had on the prior slide. Minus m tau xy minus n tau xz equals 0. And then in the y direction, we have minus L tau xy. This is also in the textbook if you don't want to write all of them down. So we have these three equations, and they all have the same variables in them, which is our stresses. And unfortunately, they all have L, M, and N in them. So they are not independent. If they only had sigma x, sigma y, sigma z, and then the other ones, the shear stresses as well, but then they had different coefficients, right? Like A, B, C, D, E, F, G, H, like they had all different coefficients, then we could solve this easily, okay? And we could come up with closed form expressions for them. Unfortunately, these equations are not independent, okay? And so based on math, since they're not independent, we can say that their coefficients have to vanish. Sorry, the determinant of their coefficients vanish. So we can go to matrices and say the determinant of the coefficients vanish. And actually, I've said this backward. I mentioned that our coefficients were the L, M, and N, and our variables were the stresses. But actually, in this case, the variables are L, M, and our coefficients are the stresses. Sorry about that. The reason I got that wrong is because I didn't look at the matrix. So if we draw that determinant, then the coefficients of all of these look like this. Minus tau xy, sigma minus sigma y, minus tau yz, minus tau xz, minus tau yz, sigma minus sigma z. Okay, so here's a determinant of a matrix, and that has to equal 0. All right, sorry for that error. So now L, M, and N are gone, and we have an expression left. If the determinant of this matrix is 0, then what's in it is the sigma we want to know. Okay, that's in the first, or that's in the middle section of each one. Right, so I'm going to underline them here, 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 and here. That's what we want to solve for. That's our principal stress. And all of the other things that we have in there are inputs, right, that we know about our stress state in the coordinate system that we've defined initially. Okay. So if we take the determinant of this matrix, you can go back and think about classes in which you've done that. We'll come up with one long expression, right, where we multiply things together, and then we subtract off the other 4 terms, and things like that. And so the expression that we get when we do that is called the general stress cubic equation. For a state of triaxial stress. Okay. And this is the equation that's going to become useful to us when we go back and talk about our bar with a cylindrical cross-section. Or sorry, with a circular cross-section. Okay. So I'm going to write that expression down. And then what we're going to do is go back and look at our bar with a circular cross-section. We're going to start slashing off terms, and then we'll be able to solve it. Okay. It is a lot of terms, but they do follow nice patterns, so that's what we're going to do. Okay, so this expression is going to be equal to 0. So I'm just going to write that at the top here. 0 is equal to, and so we're going to start out, this is a cubic equation because we had sigma in 3 terms, right? And when we're doing that, we first start out by multiplying all those diagonals together. So it's a cubic equation. So we start out sigma cubed minus sigma squared times some long coefficient, which I'll write in a moment, plus sigma times another coefficient minus another coefficient. Okay? So this is our cubic equation. Our variable that we care about is sigma that we're solving for. And so the coefficients that come in are just all of our inputs, right? So I'm going to draw those in a different color. Okay, so we have sigma x plus sigma y plus sigma z. That's our first coefficient. Our next one is sigma x, sigma y, plus, it's sort of the combinations of them. Sigma y, sigma z, plus sigma x, sigma z, and then we have some subtraction of the combinations, minus tau xy squared minus tau xz squared minus tau yz squared. Okay. So that's a little bit longer of one. And then the one on the bottom is long as well, minus. Then we have multiply all of them together. Sigma x, sigma y, sigma z, plus 2 times all the taus. Minus some combinations of those. Sigma x, tau yz squared, minus sigma y, tau xz squared, minus sigma z times tau xy squared. All right. So this is the general stress cubic equation. It's got a ton of terms. And now if we were to try to solve this, right, because if we have a cubic equation, we have 3 roots to that equation. Mathematically, one of them will be real, the others might be imaginary. But this is a stress state, right? And so this is like a physical, it's based upon physical realities, right? Stress is not a physical thing, but stress is based on physical realities like load and area, right? So all 3 of the roots we will find to this will be real solutions. Okay. So let's go back to our cylinder that we had at the beginning of class, our motivating problem. Okay, so here was our cylinder, right? It was attached to the wall. There was a torque moment applied to it, and we had some arbitrary point P that we cared what is the stress at that point. And we had a coordinate system that was kind of like Z, Y, X. Right. And so we can use our coordinate system because now we define what we want of X, Y, and Z, right? And so if that point is not at the center, it's not at the neutral axis or the place where there's zero shear stress, it's some R out from that, we can define our Z from that, right? And so because of that, we can think about our stress cube and which direction these shear stresses are acting. Okay? So we can draw our cube like this. So we'll have Z here, we'll have Y here, X here, right? So we line it up exactly the same. And if we do that, we find that across the top of the cube, hang on, let me think about this. No, along the end of the tube, right, we have a tau xy, like that. And then we must have a corresponding tau yx. Sorry. What face is that? Yes. Yx. Yeah, that's right. Okay. And so those will have the same magnitude, and I've drawn them here. And since they have the same magnitude, we can just call them the same thing. So tau xy is the same thing as tau yx. Okay. And so these are the stresses, and we have equal and opposite on the back side. So I'll just draw those like in a dashed line like that. Okay, so that's our cube. And we know from beam theory that the shear stress is going to be, in other books it's like TR over J. What we have is this moment, applied moment, times R divided by our J, which I'm not going to define here today. It's just the polar moment of inertia, right? We can plug in that equation. So really, we only have like one of these components. So most of these terms now cancel out. Okay. So we could take this general equation and just basically cancel out most of the terms. Okay. So just to be explicitly clear here, we have sigma x equals sigma y equals sigma z equals 0. We have no normal stresses. We have tau xy is equal to that term there. And we don't have any other shear stresses. So we don't have tau yz, we don't have tau xz. So those are equal to 0. Okay. So now we just start slashing. Okay. So this whole second, or this, so all of these are 0. So the second term is gone. Hello. Okay, second term is gone. So there's no top term here at all. In the middle term here, we have tau xy, so we got to keep that. But all of these other terms cancel out. Okay. And then in the last one, we actually don't have anything either, because in each of these terms there's a sigma, right? Except for, well, there's a 0 in all of them. There's no tau xy without a 0 term along with it. So everything in this last, the last term goes away. So we actually come out with something really simple. So I'll just put boxes around what we come up with at the end. So we have sigma cubed right at the top. We have that's left. And then this coefficient is left, sigma, and then this tau xy here is left. That's all that's left. Okay. So I'm going to write that on the next slide. Oops, check the time. Okay. Okay, so we go to the next slide. We get 0 equals sigma cubed plus sigma times minus tau xy squared. Okay, that's all we got. So we can solve this cubic equation. And I'm not going to, this is not like a math class where we go through all the solutions to the cubic equation, but we're going to come up with 3 roots, okay? And we're going to call those roots the 3 principal stresses. We're going to call them sigma 1, sigma 2, sigma 3. And this is what you learned back when you learned about Moore's circle, right? This is what we wanted. We usually just had sigma 1, sigma 2, and we'd use and draw them out like that. Okay, if we solve this for the roots, we come out with sigma 1 equals tau xy. Surprise, surprise. So we only have a shear stress. And sigma 2 equals 0. And sigma 3 equals minus tau xy. So these three solutions, if we substitute each one of them back in for sigma, should satisfy the equation, should be a solution. Okay? So that's helpful. Right, so you could draw the Moore's circle, and you could do that. The Moore's circle is great for things in 2D. It rarely extends well to things in 3D, unless you have a very simple stress state like the one we have here. But we're not going to do that. We're going to keep it in these 3 variables. Okay, so the last thing I wanted to cover today is the directions. So these are the magnitudes of the principal stresses. Okay, principal normal stresses. But what about the directions? What about the L, M, and N that we had? Like, I know we had to get rid of them to solve the matrix in order to come up with this generalized expression, but can we go back and figure out what L, M, and N are so we know what that angle is that we had to cut in order to figure out what direction these are actually acting in, right? So we can go back to the expressions that we had before we got rid of all the L, M, and N, okay? So this was the one for x. I'll just write it up again. It was L times sigma minus sigma x minus m times tau xy minus n times tau xz equals 0. Right, and we had 3 of these, right? If you look back in your notes a couple of lines, you will see that there's one, this was just for the x direction, there's one for y, and there's one for z, right? And that's how we got rid of the L, M, and N by saying that the determinant of all these, this matrix math had to equal 0. Okay? So let's go back, and now we determined that we actually don't have some of these components. We don't have, right, so sigma x, sigma y, sigma z, those all were 0, and tau yz and tau xz were 0. And all we had was tau xy. Right. So if we simplify those expressions down, right, the first one becomes, so I'm just going to do like a cross out here. So this goes to 0, and this goes to 0. Right, so for x, we are left with L times sigma minus m times tau xy equals 0. And we can do that for the other expressions as well. And n sigma equals 0. Okay. So now we have, since we were able to sort of cut out a lot of those constants, now we have L, M, and N, and we have our sigmas in there, okay? And so this is the same thing. This is the same kind of matrix that could be solved. So it also has 3 solutions. Okay? So it will have 3 3 L, M, and N's, okay? So we will have 3 solutions. We'll have for each direction. So for sigma 1, we will call them L1, M1, and N1, right? That makes sense. For sigma 2, right, we'd have L2, M2, N2. And then for sigma 3, obviously, we'd have L3, M3, N3. Okay. So let's look just at sigma 1, okay? We had, before, we came up with a solution of sigma 1 is equal to tau xy. All right, so it was just easy. It was just the one term. And so we have that expression, right? So we can plug that in for these sigmas here. Okay, that'll simplify things further. And the first thing we'll notice, this is actually the same for all of them, which is this third equation down here. If n times sigma equals 0, then all of the n's are 0, right? n1, n2, n3, they're all 0. So we can say n1 is equal to 0. Okay, so that's the first thing we can say. And then we can simplify the other expressions and see what we come out with, okay? And so if we look at the first expression here, when we plug it in, we'll have L times tau xy, that's our first solution, minus m times tau xy equals 0. There's tau xy in both terms. So L minus m equals 0. L equals m, right? And this is for the ones. So L and m are the same. We can add in one more thing that we have to do that we know from the unit cell. This slide is getting super busy, so I'm going to go to the next one. So from a unit cell perspective, L squared plus m squared plus n squared has to equal 1. And if we know that n1 was 0, L equal m, or sorry, L equals, m, right? That's what we got from the prior expressions. Then L equals m equals plus or minus square root of a half. And that's for 1. Okay. So for this problem, we have solved for sigma 1, sigma 2, sigma 3. So we have tau xy, sigma 2 was 0, sigma 3 was negative tau xy. Those are the roots of that simple cubic. And then for the first state, we have determined the direction. So L1 is plus or minus square root of a half. M1 was the same thing, and N1 equals 0. So L, M, and N is our vector of what direction the plane is where that principal stress is. So we didn't have to have any angle with respect to Z for this one, but we had to have an angle with respect to X and Y, right? Because those determine that's what L and M is our cosine directions for alpha and beta, okay? And so this is the full solution in 3D for that very simple stress state of an arbitrary point in our bar with a circular cross section, okay? And we can plug in the values that we have, right? This TR over J, and then we could get actual quantities for this. Okay, but this is the symbolic solution. And when you solve for a stress state, what you solve for is all of the principal normal stresses, so sigma 1, sigma 2, sigma 3, and then you also solve for the vectors for each one. So right now, we only have enough time, we have like 1 minute left. We only had enough time to solve for the first one. But then we could also solve for L2, M2, N2, okay? Which actually all come out to be 0 because of the principal stress 2 being 0. And then we could also solve for L3, M3, N3. And if you have all of those values, that's that's 12 altogether, then that's a full description of the stress state in 3D. So I'm going to leave you with that. And then I may do another example of this just so we can plug in some numbers and get a better intuition as we start out on Tuesday. Okay? I think I've got like 1 minute left, but if there are questions, I think we have like time for one. No. Okay. I don't hear any questions, so I'll see you back on Tuesday. For the second week, probably have a homework set assigned next week just to get going with it, get some grades in the books. But thanks everyone, and I'll see you at the next lecture.